Welcome. This is the introduction to section 3.3. In this section, we're going to look at how we can learn about the shapes of graphs using derivatives. So here I've drawn a generic function. We'll call it f of x. I've put a point everywhere that it has a maximum, local maximum or minimum, and then I've divided this into a handful of regions here. So I want us to think about what we can say about f on each of these regions. Okay, so f of x on this first interval, f is increasing. It's starting negative and it's getting positive. And then it switches and it starts going down on this second interval. F of x is decreasing. And then here it's going up again until it reaches this second local maximum. So f of x is increasing. And now here it's getting, on this last interval, it's getting very small. So f is decreasing. Okay, can we say something about the derivative on each of these intervals? Let's see. If we look at this first interval and we were to come to any point and draw in a representative tangent line, that tangent line has positive slope. It seems to be getting smaller here, but it still has positive slope. And everywhere we were to draw one in, we would see that the derivative is greater than 0 on this interval. We come over to this interval, draw in a small representative tangent line. It has negative slope, and the same thing would happen anywhere on that interval, so that would imply that the derivative is smaller than 0. Okay, this interval looks very much like the first one. Any representative tangent line would have positive slope, which means that the derivative is positive, and finally on the last, sorry, that's pretty messy there. The derivative is positive, and finally on the last interval, the derivative is negative. Okay, we can generalize this. It seems every time the derivative is positive, the function is increasing. The derivative is negative, the function is decreasing. So if f is a continuous function on some interval ab and differentiable on ab, then f prime greater than 0 on ab, that would tell us, implies that f of x is increasing. So if the derivative is positive, the function is increasing. We see that up here. And here, when the derivative is negative, when f prime is less than 0, we see that our function is decreasing. Okay, if f prime changes from positive to negative, so let's see, where does that happen? F prime right here, it changes from positive to negative right at this point. So the function goes from increasing to decreasing, and that means we have a local maximum. Then x equals c is a local maximum, and if it changes from negative, that means function decreasing right here to increasing, which happens right at this point, decreasing to increasing, we have a local minimum. Sorry about that. Okay, well, where are those points where it's changing? Those are critical values, right? So if we want to learn, or there where the derivative is equal to 0. So if we want to learn about intervals of increase and decrease of our function, we could start by finding its critical values. So let's do an example of that. Here's a function g. It's x to the fourth minus 4x cubed plus 4x squared. So what can we learn about it in relation to the above? So g prime is 4x cubed minus 12x squared plus 8x. Okay, let's find the critical. So this derivative is defined everywhere, so our critical numbers are going to occur when the derivative is equal to 0. So we want to know when the derivative is equal to 0. It looks like we can factor a 4x out of every term, and we'll get x squared minus 3x plus 2. And we can factor that again as x minus 2x minus 1. And so it looks like our critical numbers then are x equals 0 from the first term, 2 from the second term, and 1, or x equals 0, 1, and 2 if we want to put them in order. Okay, so in relation to this picture above, those would be the spots where we likely have a local max or min. And now we can use the derivative to determine it. So how are we going to do that? Well, these critical numbers suggest 4 intervals that we want to look at. The intervals will get broken up by each critical number. So we always start our first interval from negative infinity, and we go to the smallest of our critical numbers, which in this case is 0. We're looking at this table here. The next interval goes from that critical number to the next one, which is 0 to 1. Then from that critical number to the next one, which is 1 to 2. And then finally from the largest critical number to infinity. And our ultimate job is trying to fill in this row in our table as whether the derivative is positive or negative, because then we can learn about the function g. Okay, so let's see. Let's do that by filling in whether each piece of the derivative, so the derivative factored as 4x times x minus 2 times x minus 1. So I'm going to ask about each piece of that. Okay, so on this interval from negative infinity to 0, we're thinking about 4x. Is it positive or negative? Well, those things are all negative. Multiplied by 4 is going to give me something negative. 0 to 1, 4x, 4 times something positive. Okay, so those are all going to be positive. We have positive things multiplied by 4. Now, x minus 2. You can take a point in here, negative 1. Negative 1 minus 2 is negative. So on this interval, it's negative. Take a half out of this second interval. A half minus 2 is negative. Take 1.5 out of this interval. 1.5 minus 2 is negative. Take 3 out of this interval. 3 minus 2, that is positive. X minus 1, again, take something negative, subtract 1, negative. Take a half minus 1, negative. Now take 1.5 minus 1, positive, and 3 minus 1, positive. Okay, so now we know g prime is just the product of these things. So if I look down this first column, negative times negative is positive, times negative is negative. Positive times negative is negative, times negative is positive. We multiply 2 positives and a negative is going to give us a negative. We multiply 3 positives, we get a positive. So here g prime is negative on this first interval, which means that g of x is decreasing on that interval. Then g prime is positive, so increasing, and then negative. So decreasing, and then positive, so increasing. And now, let's see, I should have moved this table up a little, but we'll make it work. So now we change from decreasing to increasing. Decreasing to increasing means we have a local minimum at x equals 1. Here we change from increasing to decreasing. So we have a local maximum. Oops, sorry, I got that one wrong. This first one is changing at 0. So we have a local minimum at 1. Now we're changing at 1 from increasing to decreasing. So we have a local maximum at 1, and then there's one more change right here from decreasing to increasing, which again gives us a local minimum at x equals 2. Okay, so we can learn where our function is decreasing, where it's increasing, where its local minimums and local maximums occur by using the first derivative. Okay, so now the next question is, what can we say about the second derivative? Or what can we learn from the second derivative? Okay, so we're going to do something similar to the above analysis here, and then we'll put this all into practice. So what can we say about our function here? All right, well, there's two things. If our function, let's define a couple of terms. If our function looks like this, roughly, it's like it's opening down, we say that it is concave down. If it has a shape that looks like this, we say it is concave up. Okay, so let's look here. Here on this interval, our function is concave down. Here on this interval, it looks like the second picture, so it's concave up. And then again on this interval, it is concave down. Okay, now let's see, what can we say on these intervals? Well, here on this interval, this first interval, if we came down here, our derivative would be positive and really big, and then our derivative is getting smaller, and then our derivative is getting even smaller, and it gets negative before it gets here. So on this first interval, f prime of x is decreasing. F prime of x is a decreasing function. On this interval, the second interval, the derivative starts negative, and then changes to 0, and then eventually turns positive over here. So on this interval, f prime of x is an increasing function. Okay, again, on this interval now starts positive, reaches to 0, and then becomes negative and starts getting really negative. So f prime of x is decreasing here. Okay, so if the function is decreasing, we just learned above that if a function is decreasing, its derivative is negative. So f prime of x is decreasing, so its derivative must be negative. Similarly, f prime of x is increasing, so its derivative must be positive. And again, here f prime of x is decreasing, so its derivative must be negative. So it seems that if the second derivative is negative, the function is concave down, and if the second derivative is positive, the function is concave up. So if f double prime of x, or the second derivative, is greater than 0 on AB, then f of x is concave up. Otherwise, if it's less than 0, then f of x is concave down. Okay, where does these change? These points here where we're changing concavity, sorry, I should have noted this before. Where we change concavity, these are called inflection points. And they may occur when f double prime of x is equal to 0 or undefined. Okay, next statement. If f prime is equal to 0, so that's going to happen at a point like this, and here f prime is equal to 0 at this point, but the second derivative is negative, then f of x has a local maximum at x equals c. Okay, the other situation is the derivative is 0 and the second derivative is positive. So that's going to happen right here where the derivative is 0, but the second derivative is positive. And when that happens, then f of x has a local minimum at x equals c. So that's the second derivative test for local extrema. Usually we get those from looking at intervals of increase and decrease, but that second derivative test might come in handy down the road when we do things like optimization set in some context. Okay, let's look at one more function. I know this takes a while to get all these ideas down. So I've done take some derivatives for us. So here's a function x over x squared plus 1. Let's see what we can learn about it. First, its derivative, I used the quotient rule, you can check it if you want, is negative x squared plus 1. And so the critical numbers, are when negative x squared plus 1 equals 0, and that's going to happen when x equals plus or minus 1. So that gives us these three intervals, negative infinity to negative 1, negative 1 to 1, and 1 to infinity. Okay, here we go. Now we got to determine positive and negative. That's all we're trying to do is the sign on that interval. So I take something smaller than negative 1, say negative 2, square it, I get 4. Negative is negative 4, plus 1 is still negative. Take 0 out of this interval, you get something positive. Take 2 out of this interval, you get negative 4 plus 1, something negative. X squared plus 1. Well, x squared plus 1 is always positive. Square that, you still definitely get something positive. So this term is positive everywhere. Okay, so f prime is a quotient of these two things. So negative divided by positive is negative. Positive divided by positive is positive, and negative divided by positive is negative. So that means f of x is decreasing, increasing, and decreasing. So what did we just learn? F of x is decreasing on negative infinity to negative 1 and 1 to infinity. And f of x is increasing on the interval from negative 1 to 1. Let's see, we change from decreasing to increasing at negative 1, so that would be a local minimum at negative 1 comma something. And we change from increasing to decreasing at 1, so we're going up and then we turn and start going down, so that's going to give us a local maximum at 1 comma something. We fill in this something by evaluating the original function. So f of negative 1 is negative 1 over 1 plus 1, or negative 1 half. So we have a local minimum at negative 1 half, and f of 1 is 1 over 1 plus 1, or 1 half, and we have a local maximum at 1 half. Okay, so that's all we can learn from the first derivative of this function. We get intervals of increasing, decreasing, local min, local max. Okay, here's the second derivative of this function. Again, I use the quotient rule, I simplified appropriately, and here's what we get. And so this thing is going to have, we need to know now what are the critical numbers of f double prime. Okay, those are going to happen when negative 2x times x squared plus 1 times 3 minus x squared equals 0. Okay, what critical numbers does that give? This one gives us the critical number x equals 0. This gives us no critical numbers because it's always positive. And this is going to give us the critical numbers x equals plus or minus the square root of 3. Okay? Now, let's see. Now we need to determine when the second derivative is positive to determine if the function is concave up or down. So I've broken up the pieces here again. So we take negative 2, multiply it by something negative in this interval. It gives us something positive, positive, multiply by positive. So we get negative, negative. X squared plus 1, well, that term is always positive. 3 minus x squared. Let's see, let's check. Let's take something like negative 3. Square that is 9, 3 minus 9, negative. Take something in this second interval like negative 1, 3 minus positive 1 when you square it is positive. Same thing's going to happen in this interval. Take something out in this interval like 3, and again, we're going to get something negative. Okay, f double prime is a product or quotient of all of these things. So we have 1 negative and 2 positives is going to be a negative, positive, negative, positive. So this tells us f double prime is negative, tells us that our function is concave down, positive, concave up, negative, concave down, positive, concave up. So what does this tell us? It tells us that our function changes concavity 1, 2, 3 times. So we get concave up on the interval from negative square root of 3, 0, union square root of 3 to infinity. We get concave down negative infinity to negative square root of 3 union square root of 3 to infinity. And we get some inflection points, right? So let's write those down over here. Let's choose a different color, maybe green. So inflection points are when we change concavity. So our inflection points are going to have x coordinate. The first one we change concavity at negative square root of 3. Then we change concavity at an x coordinate of 0. Then we change concavity at an x coordinate of square root of 3. And now, how do we find the y coordinates of our inflection point? We go all the way back up to our original function. So now we need f of root 3 is going to equal root 3 over 4. We need f of 0 is just going to equal 0. And we need f of negative root 3 is going to equal negative root 3 over 4. So we can bring those down here. We get negative root 3 over 4, 0, root 3 over 4 as our inflection points. Okay, we can put all of these things together. We see this change in concavity here at 0, 0. We had maximums, right? Those occurred, let's go back up. We saw that our maximums occurred at negative 1 and 1. So here they are. Here's our maximum at negative 1 and negative 1. We start concave, and then we have inflection points again at negative square root of 3. So let's go back to labeling those in green. We can see a change in concavity right about here and right about here. And if you check all the intervals we got, we see that we're increasing and decreasing appropriately, and we are changing concavity. Negative infinity to 1, we're decreasing, increasing, decreasing on our intervals appropriately. Let's see. So here's decreasing, increasing, decreasing. So we should have been able to use this given information to plot these points and sketch this curve, but for sake of time, I drew it for you here using Desmos. So if you do this as you press on in the activity and you're trying to plot some curves using the first and second derivative, use the information that's given about all the intervals, the points of inflection, the local maximums and minimums. Try to go ahead and draw that graph by hand, and then it doesn't hurt to check your graph on a calculating device. So see if you can use this to go ahead and press on to the activity for this section.